Hello everyone, I'm Manuel Carneiro. I'm with the University of Coimbra in Portugal and with the Carnegie Mellon University in the US. And I'm going to discuss how we were able to create piezoresistive foams for pressure sensing based on conventional non-conductive foams. And this is a low-cost approach that allows us to create large area pressure sensing methods. So I'm going to discuss the motivation for this work, our solution, our fabrication method, and as well, I'll discuss the operation of the foam, its characterization, and some applications. So as you all know, pressure sensors have been used widely in a variety of fields, such as robotics, industry, the automotive industry, consumer electronics, and as well biomedical devices. And the fact is that we think we are able to make them cheaper, make them more comfortable, softer, and so we created this synthesis method that allows us to create foams that are low cost, that are simple to implement, that are scalable, and that are replicable. And this method allows us to create large sheets of functionalized foam that can be then diced into individual pressure sensing cells, but as well used as large area pressure sensing pads. And our method is extremely simple. We start by mixing toluene, a copolymer, in this case SIS, and carbon black for the conductive filler. And we just mix them and soak them in our pre-existing non-conductive foam. And then we press this foam. In this case, we are using two metal loaf pans that are readily available. They are extremely cheap. And so we press this conductive solution into the foam and we let it to dry, leading us to these conductive foams. In terms of operation, we are taking advantage of the foam air cells to sense lower pressures. And when we reach to higher pressures, we are working with deforming the elastomeric material itself. To characterize this sensor, we used a very simple setup with a load cell in a moving stage connected to a multimeter, and we are able to measure resistance at different pressures. And so here are the response curves for these foam cells at different pressures, ranging from 15 kilopascal to 500 kilopascal. And as you can see, there is some hysteresis, and we are trying to solve this through materials with less viscoelastic properties. So we are going to test new materials in the future. But the fact is that the response of this foam over time is quite decent. So after 100 subsequent cycles, we get a reduction of resistance from around 1000 ohms to 954 ohms. But after 2 minutes rest, this value goes then up again to around 1000 ohms. As well, this can be made better with different materials, with different elastomeric materials. And the response time is as well quite decent, of around 120 milliseconds. In terms of applications, one of the first applications we tested was for respiration monitoring. And to do this, we created a very simple soft patch that adheres to the skin. And this patch is made of two soft electrodes that are printed using a conductive ink based on silver and liquid metal. And these electrodes are printed through digital ink writing over soft TPU film. As well, we have a medical adhesive layer that allows the sensor to be adhered to the user's skin. And all these layers are pressed together through a heat bonding process. And as well, we can see from the signal that we get very decent respiration cycles that we can distinguish between them. Some tests that we still have to make regard the motion artifacts and all the usability over longer periods. Then we as well tested multi-touch pressure mapping maps. And to do this, we diced this foam. And then fill the inside of this phone with the grid of non-conductive pristine. And once again, we have our soft conductive traces that are used for the electrodes that then connect to flexible PCBs that are then interfaced with the acquisition setup. On the right side, you can see the actual pressure sensing nut. And what we observed is that by using this diced approach, where we physically separate the conductive cells, we are able to reduce these ghost touches. For instance, when using a conductive foam, when we press a cell, all the other cells around it will sense some pressure because of mechanical deformation and electrical conductivity of the foam. And when we dice it, we can greatly reduce this ghost touching, even when using this for multi-touch applications, as you can see in the plot on the right. So when comparing this with existing literature, we can see that we have quite a decent foam that originates from commercial foam and that has a good compromise between range. It can go up to 500 kilopascal, but as well it has a very fast response time of around 120 milliseconds. As well as the conductive filler we are using, carbon black, is cheaper than most other options. And as well, we have shown some interesting applications in respiration monitoring and mapping pressures in large area mats and multi-node settings. So the main conclusions here is that we have created a simple method that allows us to functionalize a pristine pre-existing foam. And the detection range is up to 500 kilopascal with a low response time. And as well, these mats are deformable, they recover their shape, and they are extremely soft and can be used in a variety of applications, such as I said, wearable health monitoring and large area pressure sensing applications. The low cost and the scalability of process that derive from the fact that we are using very simple materials, very simple equipment that is readily available everywhere, allied to the good performance of the obtained piezoresistive foam, opens doors to its adoption in large area pressure sensing applications. And if anyone of you has any ideas for some applications, we can discuss this later. So I'll have to acknowledge the Portuguese Foundation for Science and Technology, and as well the Carnegie Mellon Portugal Consortium, and finally the European Research Council for their funding. So I'm now open to any questions if you have some.